Okay, so I've turned the tape on, um, and so the big event, of course, today is going to be the test, which will be posted. If the timer is working, the test will be posted at 11:15 on Blackboard, right? And so so right when class ends, that's when you should be able to find the test. So I'll say a few more words about that in a few minutes here when we get more people signed in, and then whatever else I was going to say about homeworks. Um, this this is a couple of things that we have on the list here. I wanted to, however, go ahead and look at just one more example again, as I mentioned right before I started the tape here, of finding instantaneous rates of change by, of course, finding the slope of the tangent line, which is the instantaneous rate of change, but finding the tangent line by successive approximations through secant lines, which are getting closer and closer to the actual tangent line. That's the process that we did a couple of times last time. And just to remind us of that, I want to do it one more time. Again, we're doing it with Desmos, so it's really easy process to go through. I just want us to understand sort of conceptually what the process is, because we're getting ready to take ourselves out of Desmos and do this without Desmos. And then you really have to understand it conceptually, or you're not going to understand what I'm doing once once the Desmos is not there. Okay. Okay, so so I'll come back and answer if as soon as we finish this example and we get more people logged on. I'll come back and answer whatever questions that you want to ask me. Okay. All right. So let me just bring up the notes here. And so we were looking at this just very abstract example last time. We have this function f of x is 4 minus 1/4 x squared. So that's a pretty easy function. That's just a quadratic function. So when you graph that, you just get this nice parabola. And so it's not a complicated function at all. And so last time we answered the question really in a couple of ways there. What is the instantaneous rate of change, right, of this function at -2? In other words, what is f prime of -2, right? So one way we could try to estimate that, right, is by actually physically drawing the tangent line on the graph and then trying to pick 2 points off of this tangent line and then computing the slope between those 2 points, right? That would be an estimate for the instantaneous rate of change. But then we got clever, and we saw that we could also find that tangent line, right? Again, as I mentioned, by approximating it with secant lines that are getting closer and closer to the actual correct tangent line. And so that's the process that we went through last time. And it's kind of a cumbersome process, except when you're doing it in Desmos, you can do it very quickly. But if you were doing it by hand, it would take you a long time. But you can get an exact answer this way. And so we found last time that f prime of -2 was exactly, we thought, 1. Okay. All right. So, but I want to try that again, just to remind us of what we did with same function now, except let's try computing f prime of 4. So what is the rate of change at the input 4? Here's the input 4 down here. If I can scroll down here a little bit. Oops. What did I do with that? Here's the input 4, right? Okay. And so we want to find the rate of change, the instantaneous rate of change right there at 4. Now, we can already, without actually doing any work, we can already see, right, that instantaneous rate of change is going to be negative, correct? Okay, because the curve is decreasing here at 4. So you can just visualize the tangent line without even, trying to draw it. You can visualize the tangent line right here at 4, and that tangent line is going to have negative slope, right? The curve is decreasing here at 4. So that means the instantaneous rate of change, whatever we come out to estimate it, well, actually, I think we're going to find it exactly through the process we're getting ready to go through. We can see immediately that that's going to be negative, right? Of course, that's not a very good estimate, right? Just to say a number is negative. There are lots of negative numbers. So we're going to get a better value than this for the instantaneous rate of change. here at 4, but I did want to point out that you can already see, right, that it's going to be negative. Now, remember, in this notation, right, f prime of 4 is instantaneous rate of change, so please don't confuse that with f of 4. F of 4 is just what is the output that matches the input 4. You can easily see from the graph that that is 0, right, because 4 happens to be an x-intercept for this graph. Of course, you can calculate it too by plugging 4 into the formula, and you'll also get that f of 4 is 0. But that's not what we're interested in here, right? We're interested in f prime of 4, the instantaneous rate of change, and that's not going to be 0. We can see that's going to be negative, correct, right? Okay, all right. So again, let's remind ourselves of the process that we went through here. So let me see if I can find Desmos here. I've already got this. Graph made here, and let me move some things around here on my screen so that we can look at here's the graph. So that's a little bit obscured here, but there's the graph, and that's enough of the graph that we can see what we're doing here. And there, of course, is the input 4, right? And so remember, what we're going to do is find an average rate of change, right? Starting at 4 and then going over to 4 plus some little increment, all right? In this case, I decided to start, you can start with any increment that you like, but I decided to start with an increment of 2. So I'm going to find the, and I just chose that kind of arbitrarily. You could pick a different increment to start with. So, so what I'm going to find is the average rate of change from 4 to 4 plus 2, which is 6. All right. Now, that average rate of change from 4 to 6 is the same as the secant line that connects these 2 points on the curve, right? The point where x has the point where the x coordinate is 4 and the point where the x coordinate is 6. The y coordinate of this point just happens to be -5 if you calculated that. So I'm going to find the slope of this secant line, and that's what I'm going to use as my initial estimate for the slope of the tangent line at the input 4, the instantaneous rate of change at the input 4. So we'll know that's not a good estimate, right? Or that's not a perfect estimate, because this secant line is not the same as the tangent line, right? This secant line is a little bit too steep, I think, okay? I don't think the tangent line here at the input 4 is going to be quite as steep as this secant line. Remember, tangent lines usually will touch the graph at one point and they won't cut through the graph. Notice this secant line, usually, sometimes they do, but that's a rare instance. So notice this secant line cuts through the graph, right? It goes a little bit below the graph here from 4 to 6. So this secant line, this red secant line that I have drawn here is definitely not the tangent line. All right, now I can do that average rate of change calculation on my own because I have the formula for that. That's the sort of question that you'll be asked on a test, right? Is what's the average rate of change of this function from x equal to something to x equal something else, right? But I've had Desmos do that calculation for me, okay? So if you look here on the right-hand side, there's the point that there's the x number that I started with 4. There's my increment of 2, right? Because I went from 4 to 4 plus 2, which is 6. So I used an increment of 2. I usually like to label the increment as h. That's the traditional way it's labeled in calculus, although you could label it other things. And there is my average rate of change computation, right? It's going to be f of 4 plus 2, f of 6, happens to be -5, I can see here, right? Minus f of 4, which happens to be 0, divided by 6, 4 plus 2, 6, right? -4. Okay, so when you do that arithmetic, you end up getting an average rate of change here of -2.5. The reason I label that as m, of course, is this is an average rate of change, but it's the slope of the secant line, right? Okay, so you know, we often use the letter m to represent slope. Here it's the slope of the secant line. So the slope of this secant line is -2.5. Okay. All right, but here's the important thing, right? How did we get a better estimate, right? How did we get a secant line that looks more like the actual tangent line that we want to find the slope for? So what's the trick here? What am I going to do? So someone needs to tell me.
Zoom in.
Well, yeah, that's one process for finding the tangent line, is zooming in on the graph, right? Okay, Alva, but that's not what we have a little bit different method in this case. So what's another way of getting a secant line that looks more like what the actual tangent line is supposed to look like? What was the game that I played last time?
Was it narrow the interval?
Yeah, that's right. You narrow the interval here. Instead of going from 4 to 6, we're going to go from 4 to, instead of going from 4 all the way over to 6, Colin, we'll go from 4 to a number much closer to 4, right? Okay. In other words, what that means is I'm going to lower my increment. So instead of going from 4 to 4 plus 2, I'm going to go to 4. I'm going to go from 4 to 4 plus a number that's much smaller than 2. Colin, what do you suggest there?
0.1.
0.1, yeah, why not? Okay, that's fine with me. All right. So let me see if I can fix this. So I want to go now to 0.1. Okay, and see when you do that, see how that changes the picture. You still have a secant line here because you've got this line that's connecting 2 points on the graph, although they're very close together now, right? Okay, but now notice that secant line, it's still a secant line. It's not quite a tangent line, but that looks very much like what a tangent line would look like, right? Okay, so see this approximation for the tangent line, although it's still a secant line, is much closer to the actual secant line, I'm sorry, the actual tangent line than our first estimate. Now, Colin, if you look here, when you calculate the slope of this secant line, which is just the average rate of change starting at 4 and going to 4.1, look what we get. We get minus 2.025, okay? So this is now a much better estimate for the actual slope of the tangent line. But Colin, there's no reason why we have to stop here, right? So how can I make this even better?
Reduce the increment even more.
Yeah, you just keep reducing the increment, right? Okay, so what do you want to try now?
0.01.
0.01, yeah, okay. So let's try an increment of, oops, there's no such thing as 0.01. Let's try 0.01, yeah, okay. And there, look, those 2 points are so close together on the graph, you can't even distinguish them anymore. They're overlapping each other. And you can see that this really is a secant line here. It's the secant line that connects x equal 4 to x equal 4.01. But those are so close that this secant line looks very much like what the actual tangent line is going to look like at 4, right? And so what is the slope of this secant line? It's minus 2.0025. So a moment ago, we had minus 2.025. Now we have minus 2.0025. But now, here's what the founders of calculus said, you see, okay, right? Okay, they said, oh, there's no reason why we have to stop this process, right? We can just keep making that increment smaller and smaller as long as we like, right? So we can make this increment infinitesimally small, indefinitely small. So here I've tried an increment of 0.001, right? What is that slope of that secant line? Now it's minus 2.00025. Let's add one more zero here. So an even tinier increment. And now see, Desmos can't even distinguish between the 2 points. It thinks they're the same. They're really not the same. But in the graph here, Desmos can't distinguish them. So essentially, as far as Desmos is concerned, you already have here a tangent line, you see, okay? But it is a secant line, and its slope is minus 2.00025. Well, Colin, you can see the pattern here very clearly, right? Every time I add another zero, what's happening to my slope of my secant line? It's getting closer and closer to what? What actual
2.
value?
Well, to
what?
-2.
-2, right? Sure, right. I can keep making this increment smaller and smaller, but I can already visualize now. I can already imagine what's happening, correct? Okay, as I keep making the increment smaller and smaller, this slope of this secant line, and this secant line is getting closer and closer to the tangent line. This slope is getting closer and closer to -2. So the limiting value here, if I continue this process, right, has got to be -2. So we can deduce, right, using our human imagination, right, our human intuition, we can deduce, oh, the slope of that tangent line must be -2. That's just got to be what it is, right? So, and that's the key insight, okay? See, I can imagine, oh, as I keep making the increment smaller and smaller, all that's going to happen here are these slopes are going to get closer and closer to -2. Ooh, nice. Okay. So now I think I've answered the question exactly. You see, I think not only do I know that f prime of 4 is less than 0, I actually think it is exactly -2, which is certainly a number less than 0, right? Okay. So there is my calculation for the instantaneous rate of change at 4. By the way, another way of denoting this, the old-fashioned way, not using the prime notation, you would write dy over, it's kind of clumsy. That's why I say old-fashioned. So it's dy over dx. That also means instantaneous rate of change. And then you put a vertical bar here. Ugh, I was going to mess up that vertical bar. It's hard for me to draw vertical bars on the screen. All right, so then you put a vertical bar here, and then as a subscript on that vertical bar, you write the x value where you're computing the instantaneous rate of change, which happens to be 4. So another way of writing the instantaneous rate of change, instead of f prime of 4, you could write dy over dx at x equals 4 like that, okay? So you might sometimes see this notation. It is useful, even though it's a little bit cumbersome, that notation. All right, so let's try to write down in words. You know, it's always helpful. A big part of mathematics, although students cannot appreciate this sometimes, a big part of mathematics is writing things down in actual words, and that's a very helpful process because it really helps you think about what you're doing, okay, what you're really doing, okay. And so here was my attempt at trying to just say in words what that process that we just went through, okay, in computing f prime of 4. All right, what I think you did was we found the quote unquote limit. That's kind of an imprecise term, but we found the limit of a bunch of average rates of change, right? We found the limit of the average rate of change of that function f starting at 4 and going over to 4 plus some little increment, right? But what we did was we let that increment get smaller and smaller. So we let that increment approach 0. And what we did then is, when we let that increment approach 0, we were looking at, well, what was the limiting value, right? What were those average rates of change converging to as the increment approached 0? And we said, oh, it's pretty easy to see, right? Those average rates of change, the slopes of those secant lines were approaching -2 in this case. So the instantaneous rate of change at 4 must be -2. All right, now, maybe that's a conceptually easy process, but it's a little bit, or I hope you're understanding it conceptually. It is a little bit clumsy though, right? It's cumbersome to go through that whole process because you have to calculate a bunch of average rates of change, right? Okay, and that can be a lot of arithmetic involved in computing an average rate of change. Now we had Desmos do it for us, right? So that simplified the process, but it's still a cumbersome process. And we had to rely on Desmos. So what we want to do is, as I mentioned earlier, is we want to take the Desmos out of the process. How can we do this analytically with pencil and paper without having to rely on Desmos to do the calculations for us? And I mentioned to you last time, this is where algebra is going to really replace a lot of the arithmetic for us, okay? That's one of the great things about algebra, is it helps compress a lot of arithmetic. It helps summarize arithmetic sometimes really well. Okay, before we do that though, let me mention the test. So I think because we've got everyone who I think is going to log on. So I don't know if these are the only people who are going to take the test or what. Well, we'll see. That makes it easier for me to grade. All right, so the test will be posted at 1:15, right? Okay, and so I've already mentioned what the instructions are, right? They're going to be posted with the test. You can you can print it right on the test. You can write on your own paper if you like. You don't have to print and the test if you don't want to. You can write separately on a sheet of paper, but you will have to scan to PDF, your results, right, your answers, and then email them back to me by Saturday at 1:15. Make sure you email them to my regular university address, wallerw@uhd.edu. Do not attach the test to a message in Blackboard. Okay, so send it to via email. Make sure you put in there, this is test number 1 or something in the subject line. So I'll be sure to, find your email. And when I get it, I will confirm that I got it. I may not. It depends on where I'm at, of course, when you send it. But as soon as I can, I will confirm that I got it by replying to your email. Right? Okay. So if you don't get a confirmation from me within a day or so, then you may want to check with me and see if I really got it. And then that's how it works, right? So I will grade them and then ultimately return them to you. I don't know. I don't have a time frame for that though. Okay. The sample answers, I have already unposted those. Okay. So I've taken those down. You don't need to be looking at the sample test when you're taking the test. And I also took the video down. So you don't need to be looking at the video of the sample answers either, all right, when you're taking the test. And again, really important to show your work, right? Show a lot of enough detail to justify your answers. So make sure you show work that explains how you get from one step to another. So don't be leaving off steps. Do not be leaving off steps unless they're super trivial, okay? But if they're not trivial, you have to have them in there or I am going to count off. All right. If I'm expecting to see some work and I don't see it, then I'm not going to like that. And if I say interpret or explain or justify your answer, make sure you write that. Okay. So, because I will count off for that. That's an instruction. And if it's not followed, I will count off for that. Right. Any questions about that?
The last bit you said.
Yes.
The interpret your answer. You mean like with words?
Yes, words.
Wherever
Right.
blah blah blah, it changes blah blah blah.
Right.
Something
Exactly.
Like
yeah. Okay.
Are you will you ask us to do that? Or are we just gonna have to know?
What will I do? What now?
Like, are you gonna ask us to please write write it in words? Like, is it gonna be in the instructions, or are we just gonna have
The instruction will be interpret your answer, something like that, Donna.
Okay, cool.
Yeah, just like it was on the review.
Okay.
Yeah. Okay. So it won't. Yeah, it's not gonna say interpret your answers in words. That's kind of understood with the instruction. Interpret. All right. Interpret means explain in words, right?
Just so I know what I look for.
This is. What now?
Thank you.
Okay. All right. So yeah. So I'm just I just don't want you to overlook that that instruction, because sometimes students don't really expect that on a math test, and so they don't pay attention to it. But it's there for a reason, and I'll be looking for explanations or interpretations if I ask for those. And then also, the steps of your work, if steps are required, right? Okay. So not every question requires steps, but obviously some do. So if they're, computing an average rate of change, for instance, requires some steps. So I'll need to see that, right? Okay, those steps. So don't leave that off. So of course you're free to scribble that somewhere and then recopy it onto your test, right? That's fine. But I'll be looking for that. Let's see, on homeworks now, I will probably, let me see if I can go back to the homework. No, it's cut me off. Well, maybe it hasn't. No, there it is. Okay, so this homework, this one, I just thought it was a good idea for you to look at these problems before the test, because these have kind of like interpretations in them. So that could help you maybe with the interpretation sorts of questions on the test. But I've got this due tonight, but I'll probably move this due date. Okay, I just put it there, so I would prompt you to look at this before before taking the test, but or you can look at it while you're taking the test, but I'll probably set the actual due date back. All right, there's only 3 questions here, and they're all sort of multiple choice type questions, so it's not that it's hard to do. It's just, but I will probably move that back, so you won't be distracted by that while you're actually taking the test. Okay. Other quick questions there that you want to ask about? All right, so if you're having issues while you're taking the test, of course, email me, right? And I, I may be able to answer the question. If it's a question about, how to look at the test, or how to email the test back, yeah, of course I'll help you with that. If it's a question about a specific question on the test, you can go ahead and ask it, and but I may have to say I can't tell you that, or but if it's a question of what does this mean, I may be able to answer that. It depends on if I expect you to know what I'm asking you, or if it's a little bit vague, I can clarify things. Okay. Of course, if you think you found a mistake on the test, then let me know. Right. Okay. That's certainly possible. Okay. Any other procedural sorts of issues, or any other things on the homework? So most people are doing really well on the homework. So I'm really pleased by that. I do have some people who are not participating very well in the homework. So you're either making really low scores on the homework, or you're not starting homework assignments. So that's really going to be deadly. So you really need to be participating in the homework. That's an important part of the class. So if you're not doing the homework, try to make arrangements where you can work on the homework. Okay. All right. I think everyone's registered for the class, so it shouldn't be an issue of having access to WebAssign. So if you're having computing issues, then yeah, I know that's really vexing sometimes, but try to find a way that try to find a means for working on the homework, so you can do your assignments, because that's gonna hurt if that's not possible. Okay, all right. So I'm going to go back to the notes, and so keep in mind here what we just said. This process for finding this instantaneous rate of change, right? It's the limit of a bunch of average rates of change, right? As we go from some x value, doesn't have to be 4, it can be any x value, to an x value a little bit more than your starting x value, right? So and then looking at what happens when that increment gets small. So here's that process written in words, and I'm going to now I'm going to take that, and I'm going to take a little bit of the verbiage out of it and sort of convert it to mathematical notation, right? Okay, so that's what I'm doing in this equation here. All right, so let's look at this closely, and make sure that we kind of understand what is encapsulated in this equation. All right, so suppose you have a function. This can be, just any old function, and but now we do have to assume that the function, when we graph it, is smooth. So it can't have a bunch of corner points on it. It's got to be a nice smooth curve, and it's continuous, right? So it's connected at some input. Okay, so this input A means some number that's going to be a specific number, right, in the domain of your function. Then, if you want to find the instantaneous rate of change, okay, the instantaneous rate of change of your function at that given input, at that starting input, right? Here's what you do. So this is the process that we just went through in Desmos, but here I have kind of expressed it in mathematical notation. So, so what you're seeing in this equation now, okay, keep in mind, this kind of represents an entire process, all right? This is not static, okay? You have an equation here, but this equation is really kind of summarizing a process. So what we're going to do is find the average rate of change from that input that we're starting at, right? That input to that input plus a little bit of an increment, right? Okay, so we're going to find the average rate of change from this number to this number plus a little bit, all right? That is what this fraction is. That's just computing an average rate of change. That's the average rate of change starting at A and going over to A plus a little number, okay? So we're finding an average rate of change, or you can think of that as finding the slope of a secant line. And now, however, what we're going to do is determine, what happens to that average rate of change, right, as this increment gets smaller and smaller. So as we choose smaller and smaller increments, what is this, what limiting value is this average rate of change approaching? That is what is encapsulated in this notation in front of the fraction, okay? Right? We're trying to compute what's the limiting value, right? Or what is the limit as our increment gets very close to zero. The way you would read this off the page is, the way a mathematician would read this off the page is the limit, so LIM is just short for the word limit, the limit as h approaches zero, right? Okay, in other words, what value is this fraction getting close to, this fraction being average rate of change? So what value are these average rates of change getting close to as the increment gets smaller and smaller, closer and closer to zero? So you see that's kind of a whole process, right? You're picking smaller and smaller increments, right? Increments that are getting closer and closer to zero. You're observing these average rates of change, and you're trying to determine what value are these average rates of change approaching as the increment gets really small. That's exactly what we did there in Desmos just a moment ago. All right. So this is just kind of the mathematical description of that whole process. The great thing about that mathematical description, though, is if we think about that mathematical description, right, we don't need Desmos. Okay. All right. Let me show you why. So we can actually do this process miraculously on paper without having to really do that much calculation. Yeah, we're gonna have to do some calculation, but not that much calculation. All right. And we can, with our intuition, we can observe what's going to happen to these average rates of change as h gets closer to zero. Let me show you how. All right, so let's actually do it. All right, so let's use that same function that we had a moment ago. F of x is 4 minus 1/4 x squared. So that was the function that we were graphing. That was that parabola that we graphed just a moment ago. And I want to find f prime of 4. Remember, we already calculated f prime of 4 in Desmos a second ago. It came out to be what, -2? But now we're going to do it without Desmos, okay? And you're going to see that you really like to do it better without Desmos. Okay, well, maybe not, all right? But we can do it without Desmos, all right? By using this idea, okay? By using just this summary of that process that we just described. So we really will be going through the process, but we're not going to be going through it kind of explicitly step by step like we did in Desmos. All right, so let me show you what I'm going to write down. So f prime of 4, the instantaneous rate of change at 4, right? Okay, this is going to be the limiting value as our increment approaches 0 of these average rates of change. All right, so that's f of, the a here is 4 because that's the value that we're trying to find the instantaneous rate of change at. So the a in this case is 4. So look at that formula there. It's f of 4 plus h minus f of 4 over 4 plus h minus 4. Now, we're actually going to calculate f of 4 plus h. And of course, we're going to calculate f of 4 as well, right? But here's where the algebra that I mentioned is coming into play. Because when I calculate f of 4 plus h, notice that that has this variable in it, right? So I'm going to have to do some algebra. I'm going to have to do some arithmetic with this variable. All right, so limit as h approaches 0. That's the way I would read that off of the page. Limit as h approaches 0. All right, now let's start doing some of our calculations here, the calculations that we have to do. All right, the bottom one is really easy. You have 4 plus h minus 4, so guess what just ends up in the bottom? What's 4 plus h minus 4?
H.
Someone? H, sure, right, okay. What could be easier, right, okay? So in the bottom, you just get H. So that's what you should expect to see, all right, when you're doing these, when you're calculating these instantaneous rates of change using this process, but doing it on paper, not in decimals. This denominator is going to simplify to H, okay? All right, now, f of 4, we also know. But if you can't remember it, you can find f of 4 just by plugging 4 into your formula, right? So just plug 4 in for x in the formula. But I recall in this case, just by luck, that f of 4 turned out to be 0. Okay, let me write that over here to give myself a little bit of room. All right, so f of 4, just do that computation. In this case, it just turns out to be really nice. It was 0. So that's nice. Now, here's the tricky part, though. I have to calculate f of 4 plus h. So here's where I have to do a little bit of algebra. So I'm going to take 4 plus h, right? And I'm going to plug it in for x in this formula. All right, so you want to do this part especially carefully because it's algebra, right? And, you know, algebra, people make mistakes with algebra, including me. All right, so we have f of 4 plus h is going to be 4 minus, and then 1/4, and then plug the 4 plus h in for the x. So you get 1/4 times 4 plus h squared. All right. Well, that's not so bad, but that does require a little bit of algebra, as I mentioned, because we're going to have to take 1/4, and then we have to square out 4 plus h. So don't forget, when you are squaring 4 plus h, that means you are multiplying it by itself. So please don't write 4 squared plus h squared. 4 plus h squared is 4 plus h times 4 plus h. Fortunately, the minus 0, I can just drop the minus 0, so that doesn't matter. Don't forget now, you have this denominator, though, of h, okay? All right, so look, don't let yourself get lost now, all right, in the work here. We're just methodically simplifying this expression. We know how to do that, okay? Now, however, one thing you do have to be careful about is don't forget to keep writing this limit as h approaches 0, because this fraction is not what that we come up with here when we do this simplification. That's not really what we're interested in, right? We're interested in what happens to that fraction when h gets really small. So remember, keep writing down the limit as h approaches 0, or you'll forget what you're doing. All right, let's see now. Can I multiply 4 plus h times 4 plus h? Do that before you multiply in the 1/4. So what is 4 plus h times 4 plus h? So let's see. That's 4 times 4 is 16. That's not too bad. Then we have 4 times h. So that's 4h. And then you have h times 4 again. Well, that's another 4h. And then you have h times h is h squared, right? All of that, whoops, that's plus h squared. All of that divided by that lonely h in the denominator, which is still hanging around. So we have the limit as h approaches 0 of Now let's go ahead and you want to multiply the 1/4 through. Now we can multiply the 1/4 here. And so I get 4 minus 1/4 times 16 is 4, right? 1/4 times 16 is 4. And then you have minus 1/4, it's a minus 4. And then you have minus 1/4 times 4h. That looks like minus h, right? And then you have minus 1/4 times 4h again. That's another minus h. And then you have minus 1/4 times h squared. So that's, unfortunately, there the 1/4 doesn't go away. So you get minus 1/4 times h squared, right? Over h. Now let's see what happens here. These 4s cancel each other, so that's really nice, right? So you get the limit as h approaches 0 of there's minus 2h minus 1/4 times h squared. All of that divided by h. Now you can divide out the h. See here, this h divides into this h, and they cancel, and this h divides into this h squared, and one of the h's in the h squared goes away. So what are we left with here then? We're left with the limit as h approaches 0 of minus 2 minus 1/4 times h. All of that was algebra, right? Okay, so we just did a bunch of algebra. Wasn't hard algebra, took a little while, right? Okay, but now we've arrived at this expression. This is now, we're through with the algebra. Here's where the calculus starts, okay? Because this is what calculus is all about. Look, here's what I'm thinking. So I'm going to use my intuition here. I'm thinking, what's going to happen to this quantity, minus 2 minus 1/4 times h? What's going to happen to that quantity as h gets really close to 0? So as h gets smaller and smaller and smaller, in fact, we can think of h as being infinitesimally small, not exactly 0, but infinitesimally small, very close to 0. What's going to happen to this quantity? Donna, can you see that? So as h gets really small, what happens to minus 2 minus 1/4 times h?
That it's going to get smaller too.
Well, part of it's going to get smaller. What part's going to get smaller? Is the minus 2 going to get smaller? I don't think so, right? Because the h has nothing to do with the minus 2, right? But what part of this does get smaller?
That's multiplied by negative 1/4.
Yeah, this part, right? As h gets really close to 0, right? So h is 0.1, 0.01, 0.0001, right, etc. Then minus 1/4 times h is going to really go to what? Eventually, it's going to become what? Very close to what?
Near
0, correct, right? As h gets really small, minus 1/4 times h is going to get really small as well. So as h gets really small, guess what you're only going to get left with here?
negative 2.
Just the negative 2. That's right, okay? This part will go away, and all you'll get left with is minus 2. That's what we actually saw in Desmos a moment ago, right? Okay, as their increment got really small, we saw that these average rates of change were getting close to minus 2. Well, but here we don't have to have Desmos to know that, okay? Because just with our human intuition, we can figure out the same thing, all right? And a little bit of algebra. We can also see, oh, as h gets really small, these average rates of change have to be getting close to minus 2, right? Okay, because this term has to be getting close to 0. Oh, so there is the answer, all right? The answer to what? We've already forgotten what the question was, right? That is f prime of 4. That's what the instantaneous rate of change of the function f at 4 must be. It must be minus 2, because these average rates of change, these slopes of these secant lines are getting closer and closer to -2, right? Okay, and as we let the increment get small, and those secant lines are looking more and more like the tangent line. So the slope of the tangent line must be -2. So you see, we can do this with a little bit of algebra without having to rely on, without having to rely at all on Desmos. Now, that did take some work, okay? That did take some work, right? But it wasn't, well, it wasn't completely impossible, right? All what that we really did there was a little bit of algebra, okay? Now, you might think of that as a lot of algebra. Well, it was some algebra, all right? But that's all it required to find the instantaneous rate of change. The calculus part didn't come into the very end, okay? The calculus part is right here, where we imagined, oh, what happens when this increment gets infinitesimally small, okay? Sort of infinitely close to 0. What's happening to this quantity? Oh, it must go to -2. Wow, okay? That's pretty heavy stuff. All right. I want to try that again now, okay? So once will not do it, so we have to practice this a little bit. So now we want to find f prime of same function. We already found this last time. We want to find f prime of -2. So what's the instantaneous rate of change at -2? Remember, my function is, I forgot what the function was. What was it? 4 minus 1/4 x squared, right? Okay. So same function, but now I want to find the instantaneous rate of change. We got that last time to be, if I can scroll up here, what did that turn out? Oh, it turned out to be 1, okay? So we figured out last time that the instantaneous rate of change, here's the function 4 minus 1/4 x squared, that has to be 1. All right, so how do I start the process? That is almost 50% here of getting this correct. What do I write down first to start this off? So f prime of -2, the instantaneous rate of change at -2 is going to be, what word do you begin with?
The limit.
Limit, right. So, and you can abbreviate that slightly. Limit as the increment approaches 0 of, and it's going to be f of -2 plus h minus f of -2 over -2 plus h minus a -2, okay? Well, and this is always going to happen. The denominator is going to simplify immediately. This is really -2 plus 2. So the denominator immediately becomes h. So that's always the easy part. And the hard part is simplifying the numerator, okay? So we want to simplify this numerator. All right, so we're going to try that after the break, okay? But you can be working on that for me while we take a little break here, because I've got to have these two things, right? So I have to figure out what f of -2 is. That's pretty easy. You just plug that into the formula. So that's just going to be a number. The hard part is, what's f of -2 plus h? Because there we have to plug in the variable h also into the formula, right? And that's the part that's going to be a little bit, that's the part that's going to be a little bit messy. But it won't stay messy for long, okay? These limits there tend to simplify pretty nicely, all right? So so it's not really, it's only scary for a second when we have to first think of calculating f of -2 plus h. But let's stop there for a few minutes, okay? So we'll come back in about 5 minutes. It's about 12:20 now. Actually, it's 12:22. So we'll come back in about 5 minutes and we'll fill in this numerator. All right, so we can verify to ourselves again that f prime of -2 is what we got last time, which was 1. All right. Okay. So let me pause the recording here and then we'll come back. Okay, I'm back here, and so let's see if we can complete this one quickly. So we were trying to find f prime of -2, right? And so we had filled in the formula here, right? The equation that we need to find f prime of -2, but we just have to fill in the various pieces. Okay, so the denominator was easy to simplify. That's h, and now we know we have to calculate f of -2. So what are we going to get when we plug -2 into that function? Right? Did somebody calculate that? Did y'all plug -2 in there and compute that? Somebody have that?
3.
Is it 3? Yeah, I remember that now, right? Okay, that was on the graph too, right? Yes, I recall that. So we can fill in this part, right? We have -3, and now here's the hard part, right? So we have to compute f of -2 plus h. So let's do that off to the side rather than trying to compute it as part of our longer equation here. Let's go off somewhere and actually do this. So I have f of -2 plus h. So that's going to be 4 minus and then 1/4 of the -2 plus h squared, right? And just be careful about squaring the -2 plus h. That's usually where students are most common place where students will make mistakes. Okay, so when you square -2 plus h, that means you have to take -2 plus h times -2 plus h, right? So do that product first and then multiply in the -1/4. So we have 4 minus 1/4 and then times, let's see, -2 times -2 is +4. And then let's see, -2 times h is -2h. And then h times -2 again is another -2h. And then h times h, of course, that's the easy part. That is h squared. And you can add, of course, the -2h and the -2h together. So you would get 4 minus 1/4 times 4 minus 4h plus h squared when you add these two middle terms together. And now let's multiply in the -1/4. So I get 4, and then -1/4 times 4 is -1. That's easy. And then -1/4 times 4h, that's plus h. So that's easy. And then we have -1/4 times h squared. Not much we can do with that. Just -1/4 times h squared is -1/4 h squared. All right. So, and of course, 4 minus 1 is 3. So now we can plug all of that back into our limit here. So I have 3 and then plus h and then minus 1/4 h squared. And then don't forget this -3 that was already there from computing f of -2. Now, see what good things happen here? The 3's cancel each other. So see, that goes away very quickly. And now we're going to be able to divide that h out of the denominator. H goes into itself one time. So you have the limit as h goes to 0 of h goes into itself once. And then the h into the -1/4 h squared is like it was before. That ends up being -1/4 h because the h will cancel with the h squared and leave you just with h to the first power. So you end up with the limit as h approaches 0 of 1 minus 1/4 h. And just like before, what happens then? So as h gets really, really small, what's going to happen to this quantity? 1 minus 1/4 h. So help me with that. Someone there. Lewis, are you there? Lewis. No Lewis. So see, we got people checking out. That's a recipe for not doing well. Kevin, Kevin Arbasto, what about you? So what happens to this quantity 1 minus 1/4 h as h gets really small here?
Say again, sir.
Yeah, so we're looking for what's happening to this quantity 1 minus 1/4 h, right? As h gets close to 0. So as h gets to be a really small number, what's going to happen to this? What's going to happen to this quantity?
It would get smaller, I'm guessing, or
Well, part of it will get smaller. What part would get smaller?
the negative 1/4, or no, the 1.
No, because remember, what's changing in this quantity is h, right? So the 1 is not changing. So that's just going to be 1, right?
Okay.
But as h gets closer to 0, what's happening to this quantity? So you see, you're multiplying, right? So what's going to happen to this quantity as h gets close to 0? You know what happens when you multiply by 0?
Just turns into 0.
It just turns into 0. That's right. Okay. So as h gets really small, okay, right, as h is getting closer to 0, minus 1/4 h is essentially going to become 0, right? Because you're taking the minus 1/4 and you're multiplying it by something that's almost 0. So this part goes to 0, but this part doesn't change because it's not being affected by the h, right? So
Yes.
altogether, then what happens then?
You're just left with 0, 1.
1, exactly. That's what you're left with, right? See, that's what we're trying to think about is exactly what you said there, right? We're just going to be left with the 1 because this part is getting very, very close to 0. Oh, so there it is. That is that's our result. So f prime of minus 2, that is the instantaneous rate of change at minus 2, is what is going to be 1. That's what we had calculated last time, but now we have verified that, right? Okay, that instantaneous rate of change is 1. Great. Okay. So again, before when we found that the instantaneous rate of change was 1, we had to use Desmos to help us. But now, see, we have done all that whole process just in these few lines here. Okay. So so we've taken the Desmos out of the process. Now we can do this by hand. Okay, so so here's this definition. This definition now is the one that we can use now to this equation here is the one that we can use to find instantaneous rates of change with pencil and paper. We don't have to rely on, drawing tangent lines or zooming in on curves, right? Okay, we can do that just with pencil and paper without even looking at the graph. Of course, what's a little bit clumsy about this process is it does take some steps, right? So that seems a little bit that seems like a lot of work, right? If you have to compute a bunch of instantaneous rates of change for the same function, you're going to have to repeat this limit process over and over again, and so that does require some work, right? So that really slows us down. So let me show you how we can speed. Let me show you how we can speed things up a little bit. All right, so here's what I'm going to do. Okay, so suppose I'm going to start with a new function though. So suppose we have the function x squared plus 2x. Let me see. I think I've got that one graphed. Let me see if I have that one graphed. X squared plus 2x. Is that it? Yeah. So there's the graph of x squared plus 2x. So it's okay, so it's not all that. It's just a parabola, right? So it's not a super interesting curve, but there it is. Okay, it's not a straight line. It definitely is a curve. Okay, so it's a parabola. It looks like the vertex is right about here, right? Okay, so we'll look at that graph again a little bit later, right? So what I want to do now is I want to find some instantaneous rates of change, but I'm not going to find the instantaneous rate of change for just a specific number. So I'm not going to find the instantaneous rate of change at 2 or 3 or 4, something like that. What I want to do is try to save myself some work here in the long run. Ultimately, I'm going to try to find the instantaneous rate of change just for any input x. So not a specific input. I'm not going to choose a specific value for x, but I'm going to see if I can find the instantaneous rate of change for any input x. All right. But I'm going to go through the same process, all right, as I did in that prior problem. So I'm going to find instantaneous rate of change. I'm going to do that by finding a limit. Okay. I'm going to do that by finding a limit, but I'm not going to pick a specific value for the input. I'm going to use the variable x. Now, let's go through the process, and then we'll see what we have achieved by doing this. All right. So I'm adding a little extra layer of algebra here, right? I'm going to have to use, in my calculations, I'm going to use the variable h like I did in the prior problem, but I'm also going to use the variable x. X represents just any input to this function. So I'm not going to choose a specific value for x, but x can be just any number. So let's see, what would this instantaneous rate of change be by this limit? Remember, you take the average rate of change from starting at x and going over to x plus h, right? You start at your input, and then you go over to your input plus a little increment. But again, I'm using x for my input rather than a specific number for my input. Minus now f of x, because I'm using x as the input, over x plus h minus x. So we're actually going to try to simplify this now using our algebraic skills. And we'll be able to do this pretty easily, actually. It does take a few steps, but they're not hard steps. Again, as always there, what happens in the denominator, that's always the easy part. So what happens in the denominator there, Kevin? You just have x plus h minus x. So what does that simplify to? Easily.
One.
Well,
Wait.
let's read it. So you have x plus h minus x. So what happens to the x's?
Cancel. Oh, well.
Yeah. So what are you left with? Yeah.
Just h.
H, right? Yeah, that always happens in these instantaneous rate of change calculations, right? So the denominator just turns out to be h. All right. So that was the easy part. Now this is also easy too. Okay. We have to fill in f of x, but this is what f of x is. F of x is x squared plus 2x. So you really don't have to do any work in filling in the f of x, because that's going to be x squared plus 2x, right? So there's no work in filling in f of x. Now, however, remember, you're subtracting f of x. So you have to be a little bit careful about the signs here. So put the minus sign there, but then put the x squared plus 2x in parentheses. If you do not do that, you're going to make a sign mistake, okay? And everything will fall apart and you'll end up with a big mess, all right? So put the f of x in parentheses. Minus f of x is minus x squared plus 2x. So that's also not so hard, right? The hard part is the f of x plus h, okay? So let's see if we can calculate off to the side here. Let's see if we can calculate f of x plus h. So that means we're going to have to plug in x plus h in for x in this formula, right? So, but that's okay. We've done this now several times, so we're not going to freak out. We have x squared, so that would be x plus h squared plus 2 times x plus h. Okay. So now I have to square x plus h. That means you multiply it by itself. So don't write again x squared plus h squared. And then 2 times x plus h is pretty easy, though. You just have to multiply in the 2. So you get 2x plus 2h. Not leaving myself enough room here, but I think we can do this. All right. So now what's x plus h times x plus h? Well, that's not bad. We get what? X times x is x squared, and then you get x times h, and then you get h times x. So those are the same. So you end up with 2 h times x. So I kind of skipped a step there. X times h is hx, and h times x is hx again. So add those together, and you get 2 of those. And then you have h times h is h squared. And then don't forget, we had the plus 2x and the plus 2h. So that's what f of x plus h is. It's kind of messy there. It looks bad at start, but that's okay. It'll simplify. All right. So let's fill that in. So we have x squared plus 2hx plus h squared, and then plus 2x plus 2h. And now you're going to subtract off. Don't forget x squared plus 2x. Well, when you subtract this off, what happens? You distribute the minus sign in the parentheses, right? So the signs change, and that's a really welcome news there. So I have x squared plus 2hx plus h squared plus 2x plus 2h minus x squared now, and then minus 2x, all of this over h. And at this point, some things are going to cancel. So Daniel, what cancels here? What cancels now in the numerator?
The same values they have, the 2x and the 2x.
Yeah, this 2x goes away, right? With this 2x, and what else goes away?
And the 2h.
No, this is 2hx, and this is just 2h, so that doesn't go away, unfortunately. But something else does go away. Yeah, the x squared, right? So this x squared and this x squared goes away. So see, that helped a lot. And now you have the limit as h, again, goes to, oops, it's supposed to be a 0 here. As h goes to 0, I put infinity there. Because a lot of times we take the limit as h goes to infinity, but we're not doing that here. 2hx plus h squared plus 2h. Is that it? 2h squared plus h squared. Oh yeah, that's it. All of that divided by h. Let me scroll down a little bit. So Daniel, now help me again. Look at this. So see, this h now will divide into all of these terms in the numerator. So we can divide out this h by dividing it into every term in the numerator. So what will just get left? When you divide h into this term, what does that leave you with?
It's going to be 2x plus h plus 2.
Perfect, right. Yeah, you can divide the h into the 2hx, the h into h squared leaves you with h, and then the h into the 2h, the h's will cancel, and you just get left with 2. All right, all of that, Daniel, was just, that was all just algebra, right? But this is where the calculus starts, because now I have to ask myself, finally, I'm getting to the key point here. I have to ask myself, wow, what happens to this quantity as h goes to 0? What will be left here when h goes to 0? What are you left with?
2x plus 2.
Yeah, the h go when h goes to 0, this goes to 0, right? This doesn't go to 0, this doesn't go to 0 because they don't involve h. But that term goes away, and you're left with 2x plus 2. Notice at this point you can drop the limit because we've already considered what happens as h goes to 0. As h goes to 0, we just get left with 2x plus 2. Now, what in the world have I just figured out? I mean, what was all that work? I notice I have an x left here, right? What we just figured out is here's a formula now. Now we have a formula for finding the instantaneous rate of change just from this formula, okay? So now I don't have to, having done all this work for this function, I don't have to do that work ever again. Now, when I want to find the instantaneous rate of change, I have a formula for that. So if you want to find the instantaneous rate of change for that function, what was that? X squared plus 2x, you now have this nice convenient formula that you can use. So you never have to do the limit again. So we did the limit once here, found this formula for the instantaneous rate of change, and now we don't have to, we can find as many instantaneous rates of change as we want without ever having to go through this process again. This formula that I've discovered here, this is called the instantaneous rate of change function, or that's a mouthful, so we shorten that to the derivative function. So this is what we now call the derivative function. This is the function that we can use, the formula that we can use to find all the instantaneous rates of change whenever we need one for this particular original function f. Well, wow, that's cool. So let's try using that then. Since we went to all the trouble to discover it, let's try actually using it. So there's that formula, 2x plus 2. So here's the first question. Use the formula that you just found for the derivative function to find this derivative. Oh, so I'm using this new notation now. So what is this? This is the derivative at where? I'm just pointing to it. So say it to me there. Yeah, 0, right? Okay. So I'm mixing notations here. This is the old-fashioned notation for the instantaneous rate of change at, in this case, x equals 0. But see, now I have this cool formula. I don't have to go through that limit process ever again. I just plug the 0 into my derivative function formula. So I get 2 times 0 plus 2, plus 2, not times 2, plus 2, which is 2. So now I know that the rate of change of that function at 0 was 2, okay? We're going to look at the graph again in a moment and convince ourselves that that could be correct, but I think that's correct. All right, so rate of change at 0 was 2. Ooh, let's try that again. That's so easy. Let's add, all right, so I want y'all to answer this question first for me. Okay, I'm going to ask someone. So once I know that the rate of change at 0 is 2, once I know that the rate of change at 0 is 2, now I can answer this question. Without looking at the graph, I can answer this question. Is the function increasing or decreasing at x equals 0? So is the curve going up or is the curve going down at x equal 0? So does it look like this? Or does it look like this? Is it going up or down? Yeah, Melissa says increasing. Right. That's right, Melissa. It's increasing because the instantaneous rate of change is positive, right? Okay. And when the instantaneous rate of change is positive, that means a function is increasing. So see, I immediately now can answer this question. Even without seeing the graph, I know that the curve is going up at x equal 0. What about f prime then, the instantaneous rate of change at -2? Okay, so before, that would have taken us a lot of work, right? We would have had to either drawn the tangent line or zoomed in on the curve, or we would have had to gone through that limit process. But now all of that work is condensed now into this nice formula. Remember, now we know the formula for the derivative is 2x, what was it, minus 2? So I forgot. Now we know the formula for the derivative is 2x plus 2. And so, see, I can just use that formula now. So to calculate f prime of minus 2, I just plug that in. So I get 2 times a minus 2 plus 2, and that turns out to be negative 2, which is less than 0. So what's the curve doing at minus 2? Is it increasing or is it decreasing? So easy, right? What is it? Decreasing, right? Okay, because the rate of change is negative. Wow, let's see what other things we can answer without actually graphing. Now, this looks like a hard question, okay, but it turns out it's not. So without graphing, we want to find where is the tangent line on that curve horizontal. So without making a graph, where on that curve would we have a horizontal tangent line? So horizontal means a flat tangent line. Well, what is the slope of flat lines?
0.
0, right? Okay. So what we're asking, what we're actually asking here is, where is the rate of change? Because that's the same as slope of tangent line, right? Where is the rate of change 0? We're just I'm just asking asking that same question. Well, but see, now you have a formula. See, you have this nice formula for the rate of change, right? So to figure out where the rate of change is 0, just take your formula for the rate of change and set it equal to 0, right? And then solve that very simple equation. So you get 2x equals minus 2, or x equals minus 1. So I think we have a horizontal tangent line at x equals minus 1. So where you have a horizontal tangent line on a graph, right? Where you have a horizontal tangent line, think about when that's going to occur. That's going to occur where on a graph you have either a peak point or you have a valley point, right? Either a local maximum or a local minimum. That's where you're going to have a horizontal tangent line. So this means that at minus 1, right? At minus 1, we must have a local maximum or a local minimum. Gee, I wonder what, now we can look at the graph and figure out which one it is, right? But again, let's see how much of this we can figure out without actually using the graph, okay? So that's my next question. So I have a horizontal tangent line at x equals minus 1. So at minus 1, I have on this graph, I have a horizontal tangent line. So my question is that a local maximum? Is that a local maximum? So do I have a peak point on the graph, or is that a local minimum? Do I have a valley point on the graph? But I want to figure that out without actually looking at the graph, right? Okay, here's the clue to figuring this out. If you have a peak turning point, right? If you have a local maximum, then you know that the curve is switching from what direction to what direction. On the left, the curve has to be doing what? Going what way? From left to right.
It has
So
to
is it increasing or is it decreasing? Is what I'm asking.
increase.
Increasing, right? If you have a peak turning point, right? The curve is increasing, and then what does it switch to on this side, on the right-hand side? Decreasing, right? Yeah. If it switches from increasing to decreasing, then you have a peak turning point. If you have a valley turning point, a local minimum, it's going to switch from decreasing to increasing, right? Well, let's see. At -1, then what happened to this? At -1, what happened to this particular curve? Do I know that? Well, let's look back at our prior work. We actually do know this, because what was happening at -2? We figured that out a moment ago. Was it increasing or was it decreasing? The derivative was what? Negative, right? So that means it was decreasing. So we know over here at -2, the curve is going down. Now, what about on the other side? Well, we also figured out what? At 0, we had figured out the curve was increasing, right? Because the rate of change was positive. So over here at 0, we had figured out previously that the curve was increasing. So guess what happens at -1? What type of turning point do we have there? Is it a local maximum or a local minimum? If you switch from decreasing to increasing, only choice is what? Minimum, sure, right. Okay. You've got to decrease until you hit your minimum, and then you start increasing again. So we know we have a local minimum there at -1. Maybe that's the next question. Yeah, okay. So at 0, we know we have a local minimum. Let's look at the graph and verify that. We've already seen the graph, so you might remember the graph. Here's the graph, all right? And see, this is exactly what we predicted, right? There is -1, and see right there, we have that local minimum, correct? Because that's where the tangent line is horizontal, right there at x equals -1, the tangent line is horizontal, and we're switching from decreasing to increasing. Wow. So wow, we learned a lot of things today. Okay. Just in that example, we now realize that we've got some powerful tools here. We can figure out where on pencil and paper, with pencil and paper, without drawing a graph. Now we have some idea of where we can find local maximum and local minima, peak turning points and valley turning points. Those are usually very important points on a graph. They usually answer lots of practical questions for us. Okay, so now we have a clue as to how we can locate those turning points. Okay, when you find the turning points, by the way, you'll also then know, you'll also be able to deduce where a function is increasing, where it's decreasing. So that's another thing now that we've discovered. And we did that by finding this function. And remember, this function is called the derivative function. So that is the formula. That's the formula that you can use to compute derivatives for any x value on your original function. How did we find that derivative function? It came from, let me scroll back up here. It came from this equation, all right? That was the equation that we simplified to find the derivative function. So remember, we calculated this limit, right? With an increment, of course, like we always do when we're calculating this limit. But instead of choosing a specific number for x here, we just used the variable x, and we simplified this formula using algebra. And that gave us this nice formula that we could use to find instantaneous rates of change at any input. Okay, so wow, we just hit a key milestone here, right? Okay, this a limit, okay, is the one we can use to find a function, a formula for computing instantaneous rates of change very quickly, okay? And so now we're going to exploit that idea of using these so-called derivative functions to quickly compute instantaneous rates of change. However, remember, there is a little work involved in finding this so-called derivative function because we have to be able to evaluate this limit. And that did take some algebra, okay? So that wasn't penalty-free, that wasn't cost-free, that did take some algebra, all right? So right now, this process is does take some work, okay? So we're going to have another goal here of how can we sort of simplify this process, right? So we can find these derivative functions quickly without having to go through this painful limit process. But that is that's the basic idea of how you find derivative functions is through this limit process. All right, well, that's not on test number 1. That is for that's for another lecture. So we'll take that question up next week before spring break. It's not spring break next week, right? It's the week after. Am I right? Or have I got my timing off here? I think the week of spring break is the week of the week after. Okay, good. All right. So we have a week next week to absorb this idea. This does take. This is a very important, key idea in the course. So it does take a little while to get comfortable with it. But fortunately, as we're going to see next week, we'll find some workarounds for finding these so-called derivative functions without having to always go through this limit, all right, process. But we do need to practice a little bit first, though, before we look for our shortcuts. Okay, so I'm done with the lecture for today. Again, the test will be posted in about 10 minutes. Do y'all have any questions that you want to ask me?
The test is going to be posted in Blackboard, right?
It's in Blackboard, right? It's under the folder that says tests and answers, but the answers won't be there.
Okay.
Just the test. Okay. So, and again, if the timer
and you said when is it due? Saturday night or
Saturday at 1:15
p.m. Okay.
Right. Yeah. So you got 48 hours to 48 hours to work on that.
Yeah. Sounds fair.
Yeah. So that should be. I mean, okay. So it's not super lengthy. It's not super short either. It's going to take some work on your part. So start working on it. Right. Okay. But you'll have plenty of time to if you've been keeping up with the homeworks and you looked at the
so the test is a little big.
What now?
The test is big, like the sample test, or
it's not quite as long as the sample test. No.
Okay.
But it looks longer than it is because there's lots of graphs on it, so that takes up a lot of space, and there's a lot of blank space on the pages when I created them. So it's not. A lot of the questions don't require much computation.
And you said we could work on a separate piece of paper without needing the questions.
Right. So so you don't have to. Yeah, you do not have to print the test. So you can write your answers on a separate. Make sure you when you do that, make sure you label those things so that I'll know which question you're answering. Right. So so try to be neat so that I can read your, especially since we're doing this by email, try to be neat so that I can read stuff off the screen. It's harder to read it off the screen than it is.
We are emailing you the PDF after we're done?
You will email it to my email address, my university email address, wallerw@uhd.edu. That's in the instructions, but but so do not attach it to a Blackboard message.
Gotcha.
Email it to me. Okay.
I have a question.
Yes.
So the sample test, I don't know if I missed it, but we went over it, right?
No, we did not. I
Oh.
taped a video of that, which I have now taken down. Okay, so that video is gone. And I've also taken the solutions down, but I had those posted for like a week. So
Okay, no wonder, because I was trying to look for them just to refresh.
yeah,
But I see it now.
yeah,
Thank
yeah. So eventually I'll put those back up once the test is over with. Yeah. So because I don't want you just looking at the sample test and then looking at the test, right? So I took those down. Okay. And they will return at some time. Other questions there?
Nope, that is it. Thank you.
Okay, so well, all right, so we're done. All right, so good luck, and I look forward to getting your tests and starting to grade those. Hopefully, I'll have them graded by Tuesday, but I can't promise that. So I'm not sure how fast I will go with that. So, but I will start as soon as I will start grading them as soon as I get them. So, okay.
Yeah, good luck on your exam, guys. Have a nice weekend, everyone.
Right. Yeah. Have a good weekend.
Thank you.
Thank you.